Hope you're doing well. Welcome to today's class. We should be starting on CNS stimulants. Last time, I think we were looking at the muscle relaxants, and we were able to cover all of them. So we start on a new topic, CNS stimulants, and then we'll be remaining with one, which is the hallucinogens. So I think we are doing not very badly. Before, I think you need to give me the exact date. You say next week, but what is the exact date of the cut? Did you give me the exact date so that nijipange, because I need to write somewhere? Did you give me the exact date of the cut? I want to write somewhere. What is your exact date of the cut? Is it 90? When did you decide the exact date of your first cut? It might just be one cut. Yes, Michael. 21st, no. I was thinking 19th. 19th is when? Now 21st is too late. Because I need also to mark. And I'm also a very slow marker. When I look at the timetable, at the calendar rather. Look at the calendar. When I look at the calendar. CNS stimulants. The advantage of these topics is that they are not very difficult. They are quite easy. So we should be able to move quickly, and also this makes your work a bit easier. The only tough areas were the narcotic analgesics, but to me, these other topics are quite not really hard. So we look at the CNS stimulants. Let's first look at the definition. And we can see that these are drugs that increase the levels of certain chemicals or chemical neurotransmitters. Of course, in the brain, you have dopamine, you have noradrenaline, you have serotonin, you have GABA, and all those neurotransmitters. And each of those neurotransmitters has its own role or activity. So we are saying that the CNS stimulants, of course, they will increase the levels of certain neurotransmitters such as dopamine, noradrenaline in the brain, and increase alertness, increase attention, increase energy, and increase physical activity. And that is what we are calling the stimulation. If you want to talk about depression, when of course the levels of these catecholamines goes down, there will be decrease. Every one of this will go down. But now we are talking about stimulation, so they will increase alertness, increase attention, increase energy, increase physical activity, the heart, increase cardiac activity. The person, of course, will be sweating, high metabolic rates, and all that. Central nervous system stimulants also raise blood pressure and increase heart rate and breathing rate. So those are what we are calling the CNS stimulants. Classification, and we can classify according to those which act directly and those which act not very directly. That is the ones which act reflexly. So we look at the ones which act directly, and we have those which are corticostimulants. We are looking at the different parts of the brain. We have those which are corticostimulants. We have the xanthine alkaloids and the xanthine alkaloids. That's where we have things like caffeine, theophylline, theobromide. You have amphetamine, of course, and derivatives. Amphetamine, methylamphetamine. We have also methylphenidate and pipradiol. We will not do the pipradiol, but I know you mentioned all the others. We also have, so those are the corticostimulants. And then you have the medullary stimulants. And these medullary stimulants really do not have any role. Most of them indeed are poisons. We have the picrotoxin, we have nicotinamide, amphetamine, camphor, and carbon dioxide. So those are medullary stimulants, and we are going to talk about them. We have the spinal stimulants. Again, even the spinal stimulants are also poisons. We have something like the strychnine. We have those that stimulate the CNS reflexes. So these are the indirect: lobeline, ammonia, veratrum, and nicotine. We will really not study any of those, but we will look at most of the others. We can also classify them according to the mode of action. And analytics, I also see analytics is another name for CNS stimulants, may be divided into 4 groups. We have those which are respiratory stimulants, like nicotinamide. Of course, if you have a respiratory stimulant, it has really no therapeutic indication. Psychomotor stimulants, like beta phenyl ethylamine, the derivatives of beta phenyl amine, it should be beta phenyl ethylamine. There is an ethyl here. beta-phenyl ethylamines, where you have amphetamine, methyl, and of course the amphetamines mainly are abuse drugs. These ones are abuse drugs. They really do not have any therapeutic indication because they cause a lot of toxicity. They cause a lot of toxicity, a lot of CNS excitation, and therefore not really therapeutically important. Then you have the methyl xanthines, which we all know. We use them as beverages. We have things like cocoa, we have things like coffee and so on, and they have some degree of stimulation. And that is why most of us get addicted to tea, we get addicted to coffee, and so on. Of course, these ones, sometimes you can use them as drugs, and sometimes they are used for, even like Cafegot is used for the management of migraine. So some of the psychomotor stimulants do have some activity, and some of also the psychomotor stimulants, we use them as anorexiants or drugs that you can use with exercise and such to manage obesity. Some of them, we also use them for hyperactivity disorder. So those are the psychomotor stimulants. You have the conversant stimulants, for sure. These are the ones I say they are actually like the strychnine. We did mention the strychnine. It's a spinal, the picrotoxin, which is a medullary stimulant. They are indeed poisons. They will induce conversions. And of course, once they induce conversions like picrotoxin, strychnine, and pentyl and tetrazole, these are only laboratory drugs. We use them as laboratory drugs when we want to, like when you want to study anticonvulsant drugs, you can use these convulsant stimulants. So where you inject them into the rats, and you'd want to see whether the drugs that you are giving can stop those conversions. Then you have the psychomimetic or psychotomimetic drugs, and the psychotomimetic or psychomimetic drugs, these again are the hallucinogenic drugs. And these drugs, again, they cause hallucinations, and most of them really do not have any therapeutic indication. So the psychotomimetic for the hallucinogens, we will study them in the next unit, in the next topic, which will be the hallucinogens. So as I have said, this is not a complicated topic, and we should be able to manage it very quickly. So we have the respiratory stimulants, and these are some of the examples. And I think one of the most important is nicotinamide. So those are the respiratory stimulants. Then we have the psychomotor stimulants or central central stimulants. So that was the second category. And where we said you can have the beta-phenylethylamine derivatives. So the beta-phenylethylamine derivatives, these are psychomotor stimulants. And of course, we have amphetamine and related drugs. So this is a general structure. They are showing that sometimes you can have substitution on the phenyl ring. And of course, when we look at the SAL, we're asking ourselves, when we do substitution on the phenyl ring, what the influence on the activity? So again, on this particular, the beta carbon, this is the nitrogen alpha beta. The beta carbon, you can also have substitution. You can have a methyl group on the alpha carbon, and you can have also another substituent at that position. You can also have the nitrogen can also be substituted. So all these R's at the end of the lesson, we should be able to understand what is the influence when we do substitutions at those positions that we have shown. So for amphetamine, when you look at amphetamine, this R, where are we starting? R is a hydrogen, R is a hydrogen, R2 is a hydrogen, R3 is a hydrogen, and R4 is a hydrogen. So indeed, for amphetamine, everything indeed is a hydrogen. Of course, we've already put them for them to be beta-phenyl ethylamine derivatives with any CNS activity. If you do not have a methyl group there, the beta-phenyl ethylamine structure itself or compound itself will not have any activity. It will not penetrate the BBB because it will have very rapid metabolism. So that's why we have fixed a methyl there, because that methyl, as we're going to see, of course, blocks the metabolism of the metabolism of the nitrogen or of the substituents on the nitrogen, and therefore gives that compound some CNS activity. So that's amphetamine. When we look at dextroamphetamine, we're only saying because of this substitution, whether this is a hydrogen or it's another group, as long as that group is not the same as the methyl, as long as this is a, let's say, even if that is a hydrogen, like in amphetamine, this carbon there is chiral. Let me get my pen. So if you look at it, of course, this carbon there is chiral. And because of chirality, we will have what we already know as optical activity. We will have optical activity. And once we have optical activity, we are saying the dextroisomer has much more activity than the levoisomer. Dextroisomer has more activity. It has also lesser toxicity than the levoisomer, and that is usually what is preferred. Occasionally, you will find the less mixture because of the cost of the separation. Dextroamphetamine, and so that dextroamphetamine will have the same structure as amphetamine. It is only the stereochemistry that is different. Then we have methamphetamine, and when we talk about methamphetamine, R is a CH3. So this one of this is the one which is a CH3, otherwise everything else is the same as amphetamine. And of course, we will again look at the influence of that methyl group on activity. Then we have phentamine, and when you look at phentamine, these ones are OH, phentamine H, the R2 is the one which has a difference. So at this particular position, R2 is a methyl group, so phentamine does not have chirality because it will have those two methyl group. And then from there you have benzamphetamine, and in benzamphetamine, benzamphetamine, and if you see the benz, it means there must be the benzyl group somewhere, and you can see it is R1 here, which is a very huge group. It is the one which is a benzyl group, CH2C6H5. Everything is the same. Then chlorphentamine, when you see chloro, you know there is a chloro group, and it is that chloro group must be at position. It is on the ring, and you can see it there. It is on the ring, and R2 also, there is a methyl group because of the phentamine. Then we have the phenylpropanoamine. When you see the propanoamine, you know there is a hydroxyl group at a particular position, and that must be R3. So R3 has a hydroxyl group. Fenfluramine, and fenfluramine again tells you there is a fluorine somewhere, and you can see R4 is a trimethane. It's a trifluoromethane group. On R4, there is a trifluoromethane group, and you can tell, at least when you look at the name, you can tell which compound group. You have a group somewhere. And then, of course, you can still see it has a different group there. It has a huge group also. It has an ethyl group at position R1. And then chlorhetamine, whereby it has an OCL at the end here, R4. R4, you have an OCL, and then you have a methyl group at position R2, which is that one. So the most important here, dextroamphetamine, methamphetamine. Of course, some of these others are also important, but you will find they have also more anorexient activity compared to their stimulant activity. And indeed, because of the structural modification, some of them can be used as anorexiants because they have the substitution lowers their stimulant activity, brings in or adds on anorexiant activity or reduced appetite, and therefore they can be used as anorexiants with minimal abuse because the stimulant effect is much reduced, as we will see when we look at the SAR. Then we also have, under the psychomotor stimulants, we also have the oxazolidinone derivatives. Oxazolidinone derivatives, and you can see these here is the oxazole ring. Nitrogen, oxygen divided, of course, by carbon gives us the oxazole ring. So that's why we are calling them oxazolidinone, because, of course, also they do have that ketone or carbonyl group there. And of course, because of that carbonyl ring, they lack the other double bond at this position, and no wonder we are calling them the oxazolidinone derivative. So we can't identify the oxazole ring, we can identify the carbonyl group, and that is the origin of their name. And under that, we are going to see how this can be developed, because if you look at them clearly, they have structural similarities, although they look like they do not have a lot of structural similarities with the amphetamines, but they do, because all that has happened is that this is a beta carbon. So what happens to this pen these days? I don't know what has happened. So this here is our beta carbon. And on that beta carbon, there is this substituent. So this oxygen here is usually a substituent of this carbon. That carbon, like you have a C double bond O, and then your ring continues, whereby so that's a substituent of that carbon, and then your compound continues. This is your first, this is your of course your first carbon, that is your second carbon, and that is your nitrogen. So it is still ethyl amine structure. You can see it's still the phenyl. I don't know what has happened. What happens to this bio? What happens? So if you look at it, you are going that way. That way, you go that way up to there. You can still say you have the phenyl 1,2 ethyl amine structure. So you have the phenyl ethyl amine structure, but your beta carbon, because this is alpha beta, has been substituted. It had the carbonyl group, but the oxygen now binds or forms a cyclic ring with the terminal nitrogen through a carbon. So that's the only difference that is there. But when you look at it properly, you will see the oxazolidine and oxazolidinone derivatives are also beta phenyl ethyl amine derivatives. I repeat again, that is a phenyl ring, that is the ethyl and amine. So they are still beta phenyl ethyl amine derivatives, but where the beta carbon has the beta carbon as part of a cycling, the beta carbon and of course the beta carbon, the alpha carbon, and the terminal nitrogen are part of an oxazolidine with oxazolidinone ring with retention of activity. So I hope you can understand that we are only putting those groups that were part of the ethyl amine side chain into a ring, which we are calling the oxazolidinone ring with retention of activity. So when you look at pemolin, it is where again, so this is a substituent. So this is not part of the beta phenyl ethyl ring. This is a substituent that is on this carbon that is now being used to bridge the oxygen and the nitrogen. So that's a substituent. Kindly note that that is not part of the beta phenyl ethyl amine side chain. So pemolin is where those two are hydrogens. Tozalinone is where both of them are methyl groups. Phenolzolone is where one is a hydrogen and one is an ethyl group. We will come across them. We'll see how we can be able to get to those structures. So those are the oxazolidinone derivatives, and we can have also the morpholinones. Again, if you look at the morpholinone, remember this is still your phenyl ring. So phenyl ring, and your beta carbon here again, the beta carbon has been substituted with before there was cyclization, it had a double bond O oxygen. If you cancel that, so you cancel that, and you see there is a double bond O oxygen there. And then if you look at now, you have from the beta, that's the beta carbon, that's we are considering the alpha and beta to the nitrogen. So that's the beta carbon, that's the alpha carbon, that's the nitrogen. So we can still say they qualify to be phenyl ethyl amine derivatives. So that you can see. So that is why they correctly or rightfully belong to this class. They are phenyl ethyl amines derivatives, where again the beta carbon, the alpha carbon, and the terminal nitrogen are part of a morpholin. So this is now a morpholin ring, part of a morpholin ring with retention of activity, but we can identify the beta phenyl ethyl chain without any difficult. So again, so this is a substituent there. So it can be a hydrogen for phenmetrazine, and when it's a methyl group, is what we call phendimetrazine. Again, there are still psychomotor stimulants, and as we have said, they are phenyl ethyl amine derivatives, but with cyclization, with the ethyl amine chain being part of a morpholin ring or being part of a heterocyclic ring with retention of activity. So the other ones, the class, if you looked at the other class, so that is the phenyl ethyl amine derivatives. We have looked at all of them. And then we have also another category of the psychomotor stimulants, which is the methyl xanthines. And the methyl xanthines caffeine, actually caffeine, theobromine, and theophylline. And when you look at those three compounds, they differ. As you can see, they are purine derivatives. This is a purine. So they are purine derivatives, and they differ in the hydrogens, number of hydrogens substituted on them. So if you look at I don't know, pen used to work very well. I don't know what happened. So if you look at caffeine, on position number 1, it has a methyl group. On position number 3, all of them have a methyl group. At position number 3 and at position number 7, caffeine also has a methyl group. So it has a methyl group at position 1, 3, and 7. So it is the one which has the maximum number of methyl groups. You'd expect maximum lipophilicity, maximum penetration of the BBB, and maximum CNS stimulant activity. So if you look at theophylline, it has at position number 1 and position number 3. That is theophylline. If you look at theobromine, I've said all of them do have a methyl group at position number 3. If you look at theobromine, it has at position 7 and at position number 3. So the only difference is the extra methyl group, and the fact that caffeine has at position 1, 3, 7, whereas the others have only 2 positions. So when you look at theophylline, it has at position 1 and position 3, 1 and 3. When you look at theobromine, it has 3 and 7. So I hope that is clear. And because of those different methyl groups, there will be some slight differences in their pharmacokinetics, because we remember methyl groups do increase lipid solubility, and therefore there can be some slight difference in the way these compounds are absorbed, in the way they are metabolized, and even in the way they are excreted. Methyl xanthine, so we have examples. We already said methyl, giving us caffeine, theophylline, CH3 as R. And of course, we have said the easier way is just to make sure the nitrogen retains a methyl group, because all of them do have a methyl group at that position number 3. So theophylline having a methyl group at position 1, and then theobromine having an extra methyl group at position number that's number 1, 2, 3, 4, 5, 6, 7 at position number 7. So then you can have others whereby we are only changing the groups. But I know the ones which are most common, caffeine, theophylline, theobromine, are the most common. But the others, even as you look at it, etophyline is just okay. It has an R methyl group there, but now the R1 group is different. So these other ones are changing in the groups that they have at the particular position. Pentoxyphylline, you can see also the group is different. But the most common and most popular of this is caffeine, theophylline, and theobromine. And as I have said, theophylline, of course, is used as a drug for management of asthma. And of course, caffeine, we have Cafegot and other drugs. And of course, even in some of the over-the-counter, quite a number of the over-the-counter medications for management of like paracetamol, you can see it in combination with caffeine for management of some aches. So if we look at aminophylline, of course, you can see it is theophylline. Aminophylline is theophylline, and it is complexed with ethylene diamine. So we do complex these xanthine alkaloids because they have very low water solubility. So you derivatize them into mixtures or into complexes for purposes of improving on their water solubility. So that's aminophylline, which is theophylline plus ethylene diamine. That is another type of xanthine, and when you look at it, it is a group there which is different. Then we have another class. Now we have on a different group, because now we are finished on the psychomotor stimulants, and now we are looking at the conversant stimulants. And definitely, we are giving a compound and giving conversions. What use would it be? But as I have said, some of these compounds, they have found use as lab tools or lab drugs, which you can use in assessment of drugs. So we are using them in assessment of drugs. You want to acid drugs for their potency or the ability to act as anticonvulsants, then you can use drugs that use stimulants, which can stimulate conversions for, of course, for the poor rats. So you inject them with the convulsant stimulant, and then you try to see whether you can control the conversions with your anticonvulsant. So we have the pentyl and the tetrazole, we have the picrotoxin, we have the strychnine, and bicuculine, that one, of course, with a slightly complex structure, and fluorothiol. Fluorothiol is a very simple one, CF3CH2 or CH2CF3, which is indeed an ether. So those are some of the conversants whereby they will not have any therapeutic indications because you give them, they will just kill. Then we go to the next one, which is a psychomimetic drugs, or hallucinogenic, or psychotomimetic. Sometimes you find them called psychotomimetic drugs or psychomimetic drugs. And as I say, these are the hallucinogens, and we have a whole topic on the hallucinogens. And we have LSD, or lysergic acid diethylamide. We have the indole derivatives, where we have psilocybin and psilocybin. And these ones are formed, or these compounds, these indole derivatives, the psilocin and psilocybin, are formed by certain very poisonous mushrooms. I believe you are aware that when you eat mushrooms, you have to be very careful that you do not you choose the correct ones. You do not eat the poisonous ones, and now you know why. Because some mushrooms do produce this compound psilocin and psilocybin. These are psychotomimetic. They are very, very poisonous compounds. And then also under the psychotomimetic or psychomimetic drugs, we also have the phenylethylamine derivatives. But those phenylethylamine derivatives which will have psychotomimetic activity must be substituted appropriately. Like you can see, we have mescaline. And those ones which bring activity, you will find that the phenyl ring has been substituted at position 1, 2, position 1, 2, 3, 4, 5, at position 3, 4, 5 with methoxy group. So that methoxy group substitution increases the psychotomimetic activity of those drugs. Just give me just 1 minute. So we are saying for the psychotomimetic drugs, which are phenylethylamine derivatives, they usually will have the methoxy groups at position 3, 4, and 5. So you have the 3, 4, 5 trimethoxy amphetamine. It does have, and of course it has, so the mescaline has a hydrogen there. The trimethoxy amphetamine will have a methyl group at that position. Remember, when you have a methyl group at that position, that methyl group is usually, when this had to be an SCH2, this methyl group, which is at this position, that's where it would control. But that methyl group can also have some slight increase in lipid solubility. So we are going to look at these drugs at their own time. Psychotomimetic drugs, we also have what we call the dissociate agents. And these are the ones that make you feel like your mind and your body are not together. That's why we call them dissociate. Again, they have no use. Cannabis, this is bang. Cannabis, from cannabis sativa, bang. Of no use at all. But of course, causing a lot of mental havoc. And you have the PCP or phenylcyclidine, again of no therapeutic indication. Of course, there was one person who was telling us when they were doing their what are they call those things that they give us when they were doing their campaigns. They were trying to convince us that these things can be of any use. Surely, by the time it's of any use, it has really destroyed. Because the problem is, how will you measure? Because you see the psychotomy, some of the people want to have the hallucinogenic effect, the euphoria, and so on. So when you give this as a drug, this can be very easily abused. Even if it has very minimal advantages, the danger of abuse of that drug is very high. And that's why sometimes you keep off, because you know the society. And when you have a drug that will cause euphoria, will cause hallucinations and so on, they will abuse that drug. And of course, and that will override the benefits that you can get from that drug. So let us go back to the psychomotor stimulants or central stimulants. And we are going to start with the methylxanthines. And what is their mode of action? The CNS stimulant action is related to the ability of these compounds to antagonize adenosine A receptors. So they antagonize adenosine A receptors. They also block the metabolism of cyclic AMP and therefore bring the stimulant activity. So antagonism of adenosine receptors by caffeine promotes neurotransmitter release. That's explaining the stimulatory effects of caffeine. Also, they inhibit, especially now theophylline, it inhibits the phosphodiesterase responsible for intracellular metabolism of cyclic AMP, thus promoting the effects of cyclic AMP, which is ionotropic, chronotropic, and lucitropic. I hope you know all these effects. Ionotropic has to do with the contractility, chronotropic has to do with the rate and of contraction, lucitropic has to do with the relaxation of the heart. So they will have an influence on all these activities, and this is because they increase the levels of cyclic AMP by blocking its metabolism. Cyclic AMP is responsible for these positive effects and therefore stimulation. We have also seen they will antagonize adenosine receptors, increase the levels of the neurotransmitters, noradrenaline, and so on, and therefore give us the stimulatory effect. They are usually dispensed, as I've already said, in a variety of mixtures or complexes to increase solubility in water. For example, you have citrated caffeine, you have caffeine sodium benzoate, you have theophylline ethylene diamine, which is aminophylline. So they are not formulated just for the sake of it. They are formulated because they have got poor water solubility. So by formulating them in a manner to increase their polarity, you increase their water solubility. All xanthines stimulate pepsin secretion, so they are contraindicated in peptic ulcers. Caffeine is used in the treatment of migraine, as I have already mentioned, I think in the formulation we call Caffegot. So we are saying citrated caffeine, and I believe this is a citrated caffeine. You can see it is together with free fatty acid, and then you have the benzoate. This is caffeine benzoate, sodium benzoate. You can see that is benzoate, because caffeine sodium benzoate, and we had already mentioned theophylline ethylene diamine. And we are only saying the reason why we are formulating these drugs or these xanthine alkaloids in form of their complexes is just to increase their water solubility. Now, the relative pharmacological properties of the xanthines, we have like the structure of caffeine. I'd already said caffeine has the highest number of methyl groups, so you'd expect it to be number one in terms of CNS, respiratory skeletal muscle stimulation, but it has minimal cardiac stimulation, coronary dilatation, smooth muscle relaxation, and acting as a diuretic. Theophylline, that is how it's classified, number one in terms of cardiac stimulation and in terms of coronary dilatation, smooth muscle relaxation, and as a diuretic. Theobromine has the least CNS, respiratory, and skeletal muscle stimulation. So that's just a way of comparing their CNS activities. So we are saying caffeine has the highest CNS stimulation, and we can understand it is because it has the highest number of the methyl groups. So we are done with that. Caffeine, of course, we are saying we enjoy caffeine. Some people enjoy theobromine, being from cocoa. Others enjoy their caffeine, and so on. So that is why we do understand from that what we have learned. Because of that mild, whether mild or strong, that stimulatory effect, we get addicted. And you find people telling you, if I don't take my cup of tea in the morning, if I do not take my cup of coffee in the morning, I will get headaches. This is because they're already addicted to that stimulatory effect that is brought about by the xanthine alkaloid. So we move on, and now we look at the psychomotor stimulant, or they are still central stimulants. And of course, we are still looking at them. And this time we want to look at the second category, which is the beta-phenyl ethylamine derivatives, amphetamine and related drugs. And we had already looked at this and appreciated the structures. So structure activity relationship of central sympathetic drugs, and of course we are looking at the beta-phenylethylamine and their beta-phenylethylamine derivative. This is the second category, and of course this is our beta-phenylethylamine derivatives. So this is a beta-phenylethylamine derivative. You can see the phenyl ring is joined on the beta carbon alpha. You can consider that to be alpha carbon. That's a beta carbon, and it is a joint. The phenyl ring is joined on a beta carbon, and no wonder beta-phenylethylamine, because you can join it here. That is why we have to be very to give the specific name. You can if you don't specify, then your phenyl ring could be in this position there, and that of course would be alpha. So that's why we have to say it's beta-phenylethylamine derivative. And we are saying, when we talk about derivatizing it into amphetamine, it is on the alpha carbon. You add a methyl group on the alpha carbon. And once you do that, you're doing quite a number of things. You're introducing a chiral center, the dextroamphetamine being more active. And of course, we find the beta-phenylethylamine compound has no CNS activity, rapidly metabolized by the monoamines. But once you put a methyl group there, it blocks the rapid accessibility. It slows down the accessibility of the monoamines to the amine to do oxidative deamination. So the methyl group improves on the activity and therefore gives amphetamine ability to penetrate the BBB and to give you some activity. So the phenylethylamine, no CNS effect. Amphetamine has increased CNS rather than peripheral activity, presumably by retarding metabolism. So I've said retarding metabolism because that methyl group increases steric hydrons and blocks or reduces the accessibility of the monoamines to the amino group to remove it or to metabolize it through oxidative deamination. And therefore, it allows this compound to have high levels in the periphery. And once it has high levels in the periphery, through concentration gradient, it can be able to move, and it has good lipid solubility, move into the CNS and bring about its activity in the CNS. Phenylethylamine, a constituent of cheese and chocolate, is without central activity, and we have explained why. It's rapidly metabolized. It is rapidly metabolized or inactivated by the monoamine oxidases. The monoamine oxidases also degrade the amphetamines and endogenous neurotransmitters, and we are aware of that. They are the ones which degrade even the neurotransmitters. Branching with the lower alkyl group on the alpha carbon increases CNS rather than peripheral activity because, as I have explained, it retards metabolism. The branching generates chiral center and stereoselectivity of possible enantiomers, and we are seeing the dextro S isomer. The dextro S isomer. Remember, we do have the S and the R. The S say meaning the order of movement, the order of arrangement of the groups, starting from the highest to the lowest, is anti-clockwise, whereas for the R isomer, it's clockwise. That's the only difference. But any of them, either S or R, any of them can be the levo or dextro isomer. But in this case of amphetamine, it is the S isomer, which is a dextro, is up to 10 times as potent as the levo isomer, R isomer, in alerting activity, and about twice as active in psychomimetic activity. So the advantage is that it has higher activity. Yes, it has psychomimetic activity, but it has also very high alerting activity. So one can withstand the disadvantage because there is very high level of stimulant activity. So here we have our amphetamine, and this is our S-dextro isomer or dextroamphetamine, and of course you can have also the the R levo isomer, which has much lower stimulatory activity. The 4-hydroxylation, so we are still moving on. 4-hydroxylation of the alpha carbon, that's the hydroxylation, or the aromatic ring decreases activity as this decreases the ability to cross the blood-brain barrier. We do accept if you do hydroxylation, you decrease polarity, you decrease lipid solubility, you increase polarity, and of course you decrease the ability of that molecule to pass through the BBB. Phenylpropanoamine or norepinephrine has but 1/100, so has very low. So it's, when we don't measure, when I mention the amount, but it has very, very low ability to penetrate the BBB of it as compared to its deoxycogenol amphetamine. Deoxy means removal of that. So beta hydroxyamphetamine has very, very low ability to penetrate the BBB because of that hydroxyl group and therefore decreased activity. Halogenation, fluorine, chlorine, or bromine of the aromatic ring, again decreases the sympathomimetic activity. So if you do halogenation, again, of any of the aromatic ring, so like you remember chlorphentamine means when you halogenate, you decrease the stimulatory activity and you might increase other activities. So the chloroamphetamine has strong central serotoninergic activity. In other words, when you halogenate the aromatic ring, you decrease one activity, you bring up another activity. It means these receptors are highly selective in the type of molecules they bind. The 6-methoxy substitution on the ring tends to produce psychotomimetic. Remember, we looked at mescaline. If you look at the structure of these mescalines, they have methoxy groups on the benzene ring. So we are only qualifying and saying if you do any methoxy substitution on the phenyl ring, you will increase psychotomimetic activity. If you do halogenation on, again, the aromatic ring, you will increase serotoninergic activity, decrease stimulant activity, suggesting binding of the dopaminergic D2 receptors. That is bringing about the psychotic state. N-methylation increases activity. So again, it means N-methylation, like in methyl or methamphetamine. So N-methylation increases activity. Again, that will increase lipid solubility. But again, now if you do dimethylation, you will decrease activity. So it only allows you one methylation on the nitrogen, one methylation on the alpha carbon, and no other substitution anywhere else. If you do any other substitution, as we have discussed, you will decrease activity. Mono and substituent larger than methyl decrease also excitatory properties. We do understand when you bring in big groups, you introduce steric hydrons, and the steric hydrons now here is not helping in metabolism or in retardation of metabolism. It is blocking the way this now drug can access its receptor. So you must understand that. So there is a time when you can put a small group, you block metabolism. But when you make up the groups very large, then you find that you also interfere with the way this drug is going to anchor itself onto the receptor, or it's going to bind the receptor, and therefore you will decrease excitatory activity. But many compounds attain anorexiant. So that is important. So now when we increase the group like to a C2H5, as you see some of the I think a bupropion. Well, as you see in some of the drugs that we're going to look at, when we make the N-ARK group large, then you reduce excitatory group activity and you move on to another activity, which we call the anorexiant or appetite suppression. And therefore, you can't be able to use those drugs as anorexiant. Compound with the N-large groups are used for anorexiants with decreased abuse potential relative to amphetamine, because we are saying when you put a bigger group, it causes steric hydrons. That drug is not able to bind the stimulatory receptor, or it is not able to, because most of these drugs will interfere with, they will act like noradrenaline, they will act as dopamine. So once you may enlarge the group, it does not bind the receptors, and therefore it will not bring about any stimulatory activity. But it is coming up. It is able to bind now a different receptor to give you different activity. Mechanism of action of amphetamines, these compounds and certain of their metabolites have resemblance. They have structural resemblance to noradrenaline. You can't do the structure of noradrenaline, and you see there is some structural resemblance. Of course, the noradrenaline has the catechol-hydroxyl groups, but you know the noradrenaline is already there. So it's already there in the body, so that it does not have a problem of penetrating the membranes because it's already produced in the body. So that's why, although it is a catechol, it is already in the brain, and therefore will be able to bring about this activity in the brain. They can have complex and multiple actions and can participate in various neuronal, postsynaptic processes involving noradrenaline, such as synthesis, release, uptake, and pre and postsynaptic receptor activation. So you know about the release, the metabolism of most of these, even the catecholamines. They have to be absorbed fast. So they must be absorbed before they can be metabolized. So some of these drugs can compete with the noradrenaline for uptake for metabolism, and therefore you will have increased levels of noradrenaline not being, because most of it is not being taken up for metabolism. Because for it to be metabolized, it must be taken up first. You don't know uptake for metabolism, because they have structural resemblance. They can compete for the same transport enzymes. They can compete with the same transport enzymes, and therefore decrease the uptake of noradrenaline, and hence increase its concentration within the synapse, and therefore increase activity. They are indirect acting dopaminergic and noradrenergic agents. They increase dopamine and noradrenaline levels in the synapse. The central stimulant effect involves the dopamine system. They enhance the release of dopamine, and to a lesser extent prevent its reuptake into the presynaptic terminals. So what we are saying is that they are having an influence on the stimulatory neurotransmitters, increasing their levels in the brain, decreasing their metabolism, increasing their levels in the brain, and therefore bringing about stimulatory activity. Let us look at some of the members of the central sympathogenic drugs. We are looking at some of the members here now, and like earlier, of course, we have looked at the xanthines, but it's because some of this, as we move on, some of them can be used as drugs, especially as the anorexins and so on. So it has a chiral center, as we have already mentioned. That is our chiral center. The racemic mixture has higher properties of cardiovascular effect than the dextro isomer. So it has cardiovascular when you give it as a racemic mixture, because the levo isomer has higher CVS effects, and therefore not very good for therapeutic use. For most medical uses, the dextro isomer is preferred. That is the dextroamphetamine sulfate. Again, you can see we give them a salt to increase their solubility and therefore their absorption. Dextroamphetamine with the S configuration has less cardiovascular effects than the Rivo R isomer. We have said that, but it is also 10 times as potent in alerting and twice as psychomimetic agent. So of course it has more psychomimetic agent, has very good CNS stimulant activity, and has lower CVS activity, and therefore it is a better choice. But if you give them as a racemic mixture, you'll be somewhere in the middle. The methyl group retards but does not, of course, terminate metabolism by monoamine oxidase. That is oxidative deamination. We've already said that. So we are saying that methyl group, which we put there, we add to the phenylethylamine, retards metabolism. You get higher concentrations in the drug. Of course, also has slightly higher lipid solubility. We can be able even to move into the brain, as we have said, through concentration gradient. It is metabolized by oxidative deamination to the phenylacetone and ammonia. Phenylacetone is further metabolized to benzoic acid. So this is just looking at its metabolism. So we have the amphetamine there. It can undergo oxidative hydroxylation of the ring. And if that happens at para position, you can get the para-hydroxyamphetamine. It can also undergo oxidative deamination. Of course, here this one is catalyzed by cytochrome P450 or mixed oxidases. This one is catalyzed by monoamine oxidases. Now, this hydroxylation, so this oxidative hydroxylation to give us the hydroxy again, and hydroxyamphetamine. This is the one which is now catalyzed. This is the one which is giving us the benzoic acid. So this is the one which is catalyzed by monoamine oxidases. First of all, so you remember there will be the ox. This is just a very temporary, very unstable intermediate. You have the hydroxylation to give hydroxyamphetamine there, and then it undergoes spontaneous degradation. That will be spontaneous because you can see it's very, very unstable to give us the phenylacetone, which we mentioned there, and of course ammonia. So the phenylacetone, and that phenylacetone can undergo further metabolism through oxidation of that group there to give us hydroxyketo derivative, and then the hydroxyketo derivative can undergo spontaneous. That means you can also say it's unstable. Can undergo spontaneous phenylacetone, is metabolized, can be further metabolized fast to that hydroxyketo derivative, which can then further be metabolized into the benzoic acid. So that is the metabolism of amphetamine. But we are saying, indeed, amphetamine is an abuse drug. It's a street drug. You find it in the street because it is causing that stimulatory effect. Then we have the methamphetamine. And as we have said, the only difference between amphetamine and methamphetamine amphetamine, we are saying it's only the methyl group, which N-methyl group, which has been added. It has more central activity and more abuse potential. Of course, the more the central activity, the more the abuse potential. Methamphetamine is an addictive stimulant drug that strongly activates such a system in the brain. It is chemically related to amphetamine, but the central nervous system effects of methamphetamine, of course, are much greater. Both drugs have some limited therapeutic uses, primarily in the treatment of obesity, but you will not there. Is made in illegal laboratories and has a high potential for abuse and addiction. We have already mentioned that N-methylation of amphetamine increases the activity, the CNS activity of amphetamine, and therefore that is why the methamphetamine will be more liable to abuse than even amphetamine. And we have the street methamphetamine. It is referred to many names, and you find it can be called speed, meth, chalk, and so on. So those are some of the names that you find in as street names. Hydrochloride clear, chunky crystals, dissembling ice, which can be inhaled by smoking, and it is referred as ice, crystal, glass, and tina. So those are some of the names that you will find in the street, and we are saying that that drug, because of its much higher rapid CNS stimulatory activity, you will find that it has much higher abuse potential than even amphetamine. Then the chlorphenamine hydrochloride, and we remember we did mention chlorphenamine will have a parachloro group. It will have another extra methyl group, so it will not even be chiral. It is a chiral because it has the two methyl groups. Has strong serotonergic activity and is an effective anorexant with less abuse potential than dextroamphetamine. So this chlorphenamine can be used as an anorexant or for management of obesity. The major medical uses of these types of drugs includes narcolepsy, Parkinson's disease, attention deficit disorders, and although not the preferred agents as anorexiants, because we are saying they will still have a residual stimulatory effect, and therefore they are liable to abuse. More often than not, one is advised not to take drugs for obesity, but to do diet control, to do a lot of exercises. But of course, quite a number of people want to do it in a hurry. Narcolepsy is where you fall into deep sleep. You just go out of control and fall into deep sleep. We have already mentioned Parkinson's disease. Then we have methylphenidate, hydrochloride, also within the same class. And if you look at it again, you have that ring there, beta phenyl, coming that way, 1, 2. So if you look at methylphenidate, it has a slight structure. It has that group there, an ester substituent at that position. And again, you can see this is a piperidine ring. But again, when we look at it, we can appreciate the phenylethylamine structure. I hope all of us can appreciate the phenylethylamine structure. I'm trying to look for this pen. I don't know why to these days it's behaving so strange. So again, you can look at this. I don't know where I'm going wrong, because when I try to get the pen, so this phenylethylamine, you can see that that's a phenyl ring, and we move phenyl ring and we move all this way up to there. If you see all that way, that's a phenylethylamine, the phenylethylamine chain. So again, we are only talking about the terminal nitrogen and the alpha carbon. This is the alpha carbon and the terminal nitrogen being part of a piperidine ring. This time the beta carbon is out, but again also substituted to give us methylphenidate. It has 2 chiral centers. Of course, if you look at it, you can see this is a chiral center there, and that is a chiral center there. So it has 2 chiral centers and have 4 possible isomers. And of course, when you have the 4 possible isomers, remember you have the trio and the erythro and trio isomers. So methylphenidate has 2 chiral centers. The trio resmate is about 400 times as potent as the erythro resmate, and it is a marketed compound. So the trio, the erythro, sorry, is the trio is the one which has more activity and is the one which is marketed. So the D trio has much greater activity than the L trio and much more activity than any of the erythros. So the D trio we have done. So the D trio, I think of course we did the erythros and the trios, and we know when the hydrogens are on the same side and the hydrogens are on opposite side, that will give us the trio and the erythro. So that again, because of the two chiral centers, remember whenever you have like this carbon here, because of the ring, it will also behave. After all, it even has a 4 substituent, but you find sometimes even when it doesn't have 4 substituent, because of the ring, it just result in rigidity. Rings bring in rigidity and do not allow for movement. But so we are again, that is methylphenidate. And how does it work? It's protonated. Protonated methylphenidate resists ester hydrolysis, because you can see we have a danger. This is an ester, as I had already mentioned. And we have very high level of esters in the body. Very high level of esters in the body. Esterases, sorry, very high level of esterases in the body. So you'd expect this ester to be rapidly metabolized. And indeed, it is rapidly metabolized. And when it's metabolized, it gives you the acid, and the acid does not have any activity. So what we are saying is that in the body, because this nitrogen is basic, it will be protonated. And this will carry a positive. So the protonated methylphenidate resists ester hydrolysis, and therefore you will, even if there will be some hydrolyzed, you will get a little bit remaining, and whatever amount remains is able to penetrate the BBB, get into the brain, and is also hydroxylated into the hydroxy methylphenidate, which has a better activity. So in the liver, so it is protonated. Protonated methylphenidate resists ester hydrolysis in the GIT and is well absorbed. In the liver, it is hydrolyzed into the inactive Ritalin acid catalyzed by inactive Ritalinic acid catalyzed by the carboxy esterases. We are saying, of course, the esterases are the ones which you bring as Ritalinic acid, and the Ritalinic acid, of course, is not active. Also metabolized into the cyclic amide by liver microsomes, but small amounts, this is what is important, small amounts that cross the BBB is metabolized in the parahydroxy methylphenidate, which is also active. Methylphenidate is active, and also the hydroxy derivative is also active. So we are saying very little passes through the BBB, but that little is enough to give us the stimulatory activity that we are talking about. I can't enlarge it much. So what we are saying, you have the methylphenidate there. That is a methylphenidate. You can see, I hope you can see, this is our ester, because I've tried to enlarge it, unfortunately. Okay, I think that's much I can. So that is our methylphenidate. And it can undergo ester hydrolysis. So it can undergo ester hydrolysis to give us the Ritalinic acid. You can see this group here is just carboxylic group, COH, Ritalinic acid, through ester hydrolysis. Then it can also undergo, this is what, where is this? This is microsomal. This microsomal oxidation. Again, if it does that, it's just this oxidation there at that point. So microsomal oxidation. And then this is what has happened here, this carboxylic group, ester. Oh, so this now, it has undergone microsomal oxidation, and then it has gone hydrolysis, ester hydrolysis. So you can see this compound, sorry for my not very clear compound, but here this is a carboxylic group there, and it has been oxidized there. So we are calling it oxo-Ritalinic acid. So oxolitolinic acid. It is oxolitolinic acid. First of all, there was oxidation, microsomal oxidation, to give you, initially it must be a hydroxyl group and then oxidized to the oxomethyl phenidate. So that one, the hydroxyl group oxidized to the carbonyl group to give us the oxomethyl phenidate, and then and then hydrolysis of the ester group. Now it ceases to be methylphenidate and becomes oxolitolinic acid. So that is that one there. And then we have also said that that's just hydrolysis. And then you can have, again, also microsomal oxidation. This is now microsomal oxidation. So the microsomal oxidation can be of two types. There can be the microsomal oxidation that oxidizes the piperidine ring. And this is because this carbon here is ortho to the nitrogen, and therefore it can undergo oxidation. So there can be microsomal oxidation of the piperidine ring, and there can be microsomal oxidation of the aromatic ring. So you can have microsomal oxidation of the aromatic ring, and then hydrolysis. So this microsomal oxidation followed by hydrolysis, and this gives us para-hydroxylitolinic acid. Para-hydroxylitolinic acid. This is para-hydroxymethylphenidate. So it's metabolism not very hard. One, I repeat again, it can undergo ester hydrolysis to give us litolinic acid, which is not active at all. It can undergo microsomal oxidation to give us para-hydroxymethylphenidate, and that can undergo further hydrolysis to give us para-hydroxylitolinic acid. You can also have also microsomal oxidation of the piperidine ring to give us the oxiderivative of methylphenidate, and that can also undergo ester hydrolysis to give us the oxiderivative of course, of the piperidine ring of ritolinic acid. And all of this can also undergo wherever you have a hydroxyl group. Wherever you have these compounds can also undergo glucuronic conjugation. They can undergo glucuronic conjugation. They can be excreted the way they are, or they can undergo glucuronic conjugation. The minute they are conjugated, then they have very high water solubility and rapid removal from the body. And this but this one is not as detailed as what we are looking at. So we are saying this group there can undergo hydrolysis to give us litolinic acid, which is inactive. All the little that passes after protonation of the nitrogen passes into the BBB can be metabolized to the para-hydroxy metabolite or para-hydroxy methylphenidate, and that, as we have said, together with methylphenidate are responsible for the stimulatory activity. Mode of action?
Hello.
Yes.
Please,
Yes.
can you go back to the metabolism slide kindly?
All right, no problem. I know it was this one.
Yes.
Yeah.
So on that, from methylphenidate to para-hydroxymethylphenidate,
Yes.
I think the hydroxyl group is not at the para position. I think it's at the meta position. It should be maybe in the para.
Yeah. So it should be. Let's see. Ortho meta. Although it should be here. Yeah. Thank you for that. It should be in the para position. Let us see the other one. Thank you. Let us see this. Yeah. It should be like this. At least it's corrected here. It should be. This is our ortho meta para. Ortho meta. Correct. It should be at that position. Thank you for that. So correct it in your. So it should be this is ortho meta. It should be at this position. Sorry about that. Be at this position. I didn't. So it should not be there. Cancel it there and put it there. So. Asante sana. Thank you very much. So it should be para. The name is para. The person who was drawing it, because I didn't draw it again. I just looked at it from some place. So it should be in the para position. But this one is ortho. This is also meta, because if you are looking starting from this position, it is, of course, but we are considering it is ortho to the amino group, because the amino group is an ortho para director. So it can be able to direct the hydroxylation at that position, and then of course oxidation to the ketone, and that's why we are calling it oxo-retinoic acid. Thank you about that correction. So we are looking at the mode of action, the methylphenidate or its para-hydroxy metabolite, or even both. They can block noradrenaline uptake. As we said, if they block noradrenaline uptake, that is by competing. They will compete for the uptake for the enzymes. Now, in fact, usually it's an active process. They will compete for those enzymes, and once they compete, if the noradrenaline is not taken up, then it does not undergo metabolism. They can act as postsynaptic agonists. There is structural similarities, and therefore they can act as agonists. They can deplete the stored noradrenaline pools as recipe. In other words, when they are taken up, they can also go into the pools where the noradrenaline is stored, get inside there, push out the noradrenaline, and cause that excitation. They can block also dopamine reuptake for metabolism. So those are some of the ways they can be able, the methylphenidate or the parahydroxy metabolite can bring about its activity. It is used to treat attention deficient hyperreactive syndrome, and this is mainly, especially in children who are so active and so restless. They cannot concentrate in anything. It also happens in adults, because I think it's not complete. When you get it when you are a child, it never clears. So even when you are an adult, you still have the problem where you are highly active. You cannot, yes, you are active, but you do not have attention. You cannot concentrate on anything for reasonable time. So like if you are in class, the way you are in class, within a short time, you are not able to concentrate. So we are talking about, can be used for attention deficit hyperactivity disorder. Methylphenidate is also used to treat narcolepsy, and narcolepsy, as I had said earlier, it's an uncontrollable desire for sleep. Not just desire, it's an uncontrollable sleep. You don't just decide to sleep, you sleep, or a sudden attack of deep sleep. So it's a desire or a sudden attack of deep sleep. And that means you can go anywhere and you are seated down and you just sleep. So that is what we can call narcolepsy. And we even say most of these stimulants, most of these psychomotor stimulants are used for that condition. So that is now methylphenidate. And again, we are still moving on, and now we want to look at the derivatives of cat. I believe you know what cat is. Cat is miraa. Kitu watu wanaendanga wanachew kama ng'ombe. Na unaona, you look at a person, they look so ugly when they are chewing, they are salivating, they have to keep having bubble gum in their mouth. Very, 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 very ugly. Very ugly practice. Very, very ugly practice. But again, remember, cat is addicting. So once you get used to it, too bad. You don't care. You keep chewing, irrespective. Sometimes when the urge comes to chew, or you see the content of the stimulant has gone down, you will not care where you are. You might just excuse yourself a bit to go to the toilet. And what you do want to go and do is that you have those mirrors in your handbag or wherever you have put them, and you won't go and chew. So we want to understand what is that which is in mirror that causes people or causes the addiction. And indeed, it is the compounds that are found in mirror are compounds that cause stimulation. They are stimulated, they are psychomotor stimulants, and therefore will cause also addiction. So cat, it is used for its central stimulant action. It contains what we call cathinone, which is an oxoamphetamine. So of course, because it is not, you see, with oxoamphetamine, it means it has oxygen. So it will have lesser stimulant activity than amphetamine, but it still has some stimulatory activity. It is potent. It is as potent as amphetamine as a central stimulant. So it has that oxygen, but incidentally, they are saying it is as potent as amphetamine, and that is why you find, and I don't know why it's really, it's like it is allowed. It is like it's legal. So we have the cathine, but this time, so when we have the hydroxyl group would have much more. Hydroxyl group would have much more polarity. polarity. So when now you oxidize it into the carbonyl group, you decrease the polarity a little bit, and this compound is said to have very good activity and can be able to penetrate the BBB and give us a lot of stimulation. So what is found in cathinone is not amphetamine. What is found in cat is not amphetamine, but cathinone, which is also a very potent stimulant. Central stimulants, phenmetrazine or 3-methyl-2-phenyl-morpholine is obtained by ring formation in cathinone structure. So if you look at this even before we discuss, so you see this is where I was trying to explain how you can get the cyclization. So if you look at cathinone, this group here, the beta carbon has an oxygen. So all that happens is that this oxygen is joined to the terminal nitrogen through an ethyl group, joined to the terminal nitrogen through an ethyl group. So if you look at your structure, the structure still continues. So if we look at our structure, the structure still continues. I have to know must know what is happening, because there must be something. I'm losing this pen. So if you look at this, that is so the phenyl ethyl amine. So the phenyl ethyl amine, the oxo group or the carbonyl group interact or bind or react to the terminal amino group through an ethyl chain to give us now this. So this is our added group there. And that is what we call phenmetrazine. And if the hydrogen here is replaced by a methyl group, we call it phendimetrazine, if that is a methyl group. So you can see, therefore, there is structural resemblance between cathinone and phenmetrazine, whereby both the beta and alpha carbon and terminal nitrogen are part of a morpholine ring, again with retention of activity. So it is also related to the compounds. We also have the compounds we are calling pemolin, and when we look at pemolin, you see now pemolin is not a 6-membered ring, but it's a 5-membered ring, and we had looked at it. But again, it still has activity. It is related to pemolin, which is an alerting agent used for, again, attention deficit disorder. So again, when we look at the morpholines, you have phenmetrazine, where this is a hydrogen, and we have phendimetrazine, where that's a methyl group. But when we look at these structures, we are able to see that they are beta phenyl ethyl amine derivatives, where the oxygen substituted as a beta carbon becomes a part of the ring, or you have a morpholine ring becomes part of the ring, giving us a morpholine ring, where also the beta, alpha, beta, and terminal nitrogen are part of the heterocyclic ring with retention of activity. So even when you look at that structure, you can see this is a phenyl ring. You can be able to explain why this compound has activity. It has structural similarity with the phenyl ethylamine, and therefore can still interact with the receptor. The phendimetrazine stimulates the central nervous system, nerves and brain, which increases your heart rate and blood pressure, and increases your appetite. So it can also have some anorexiant activity. It is a prescription medication that is used together with diet and exercise to treat obesity. And then also we see pemorine. Again, even pemorine is the same thing. We have this one as a double bond there, and our structure continues this way. But now again, the oxygen connects with the terminal nitrogen, this time through a methylene group. The other one was an ethyl, an ethylene group. This is a methylene group. The other one, we had 2 carbons. And then you can have substitutions on that carbon with retention of activity. So when that happens, you can see we are having an oxazole ring. This is what we call the oxazolidine ring. So we are having an oxazole ring, and in the other one, we were having a piperidine ring. So, but we can't be able to understand the origin of these rings. And of course, when we have this, it allows this carbonyl group, it allows for ketoenotautomerism, where this oxygen can exist either as an alcohol or a carbonyl. So this is just ketoenotautomerism, which can occur because of the fact that you have that hydrogen there, that you can lose that hydrogen, the electrons coming in there and now going out. So that is just the tautomers to show that it can exist in equilibrium. And when we look at aminorex and pimolin, what is the main difference? That is real. Oh, it's only this group there. So that where aminorex does not have the ketone or the oxo, it's not an oxo derivative, and the pemolin is an oxo derivative. So I'm only showing you because sometimes you see these drugs, you can understand that they are related to cathinone, they are also related to the phenylethyl amine structure, but they are recyclization. It is just cyclization. And again, when you look at those, the kind of drugs you can have pemolin, where both of these are hydrogen. You can have tozalinone, where they are both methyl groups. You can have phenozolone, where one of them is a hydrogen and the other one is an ethyl group, just as we had said earlier. Those substitutions, just as we said with the other groups, when you have, of course, one substitution, when you don't even have any one, if you have one substitution, you'd expect that you have good activity. When you have more substitutions, you'd expect that there will be steric hydrons, just I believe as we had discussed earlier. Pemolin is used to treat children again with attention deficit hyperactivity disorder, which we have mentioned just like with methylphenidate. It increases attention and decreases restlessness in children who are overactive, cannot concentrate for very long, or are easily distracted and are emotionally unstable. So that condition, the ADHD, is not a very good, of course, it's quite a pathological condition, has been withdrawn in some countries because of liver toxicity. That is the pemolin. It can cause liver toxicity and has been withdrawn some of the countries. Tozalinone or dozalinone, it is the same compound, is described as a dopaminergic stimulant and likely acts by inducing the release of dopamine and to a minimal extent adrenaline. Similar to analog pemolin, it is similarly void of abuse potential and like common psychostimulants that increase catecholamines. So somehow, although it is inducing the release of these drugs, it has less abuse potential, and when they have less abuse potential, you can be able to use them more as drugs, because of course you still have some of those issues, but not to a very elaborate extent. And you can be able, of course, to use them also as drugs. You can be able to use them as anorexiants, or you can be able to use them for the management of ADHD or even narcolepsy. The last one, the diethyl propion. If you look at the diethyl propion, this is its structure. And once you have the diethyl propion, again, it has borrowed its structure from cathinone. You have seen that, and of course from amphetamine. You can see that methyl. But now the nitrogen, highly substituted with large groups. And we did mention, if you substitute the nitrogen with large groups, what do? You decrease stimulatory activity, you increase anorexic activity. So that's something we have discussed. And we have seen it along the way, because when we increase substitution, as we have said, even of these drugs, when you increase the substitution here, then you also do have the same effect. So we are saying, when you look at diethyl propion, these large groups there will help to decrease the stimulatory activity, increase the anorexic activity, and therefore diethyl propion is also a drug that is more used as an anorexic, and it has lower abuse potential. It is a stimulatory agent which is structurally related to cathinone, possesses a benzyl keto group, that group there. The drug has fewer sympathomimetic, cardiovascular, and CNS stimulatory effect compared to amphetamine. It is used as an anorexant. The larger N-ethyl subsequent decrease sympathomimetic and CNS stimulatory effect compared to amphetamine. That we had already said, that you can't do N-methyl or N-methyl alkylation. But when you increase the group from methyl to ethyl, or when you do N-dialkyl substitution, you decrease the stimulatory activity, and you can increase other activities like the serotonergic activity. And that is how this compound, the diethyl propion, has found some used as an anorexiant. But we are saying for anorexiant activity, use of drugs would be almost to me like an abuse of a drug, because most of these drugs, though we are saying they have lower stimulatory activity, they will still have some of those side effects. And for obesity, the better option is to do dietary control and, of course, to do exercise if the body allows, because, of course, there are those, of course, will have other pathological conditions and might not be able to do a lot of exercises. But it's better to have dietary control and other controls rather than use drugs, because these drugs, as we are saying, they must penetrate the the BBB, they get into the brain, they will definitely also have many other toxicities, even as they give you the anorexiant activity. And I think with that, I hope I've not moved too fast. We are done with the CNS stimulants. Any question? Any question? And starting from phenylethylamine, and you put a small alkyl group at the alpha position, you get amphetamine. When it's a small alkyl group, that methyl group will introduce steric hydrons. When we talk about steric hydrons, it is where that group, if you look at that group, it will have, remember the way we used to draw those orbitals. So it will have electrons on all those groups. If you can be able to draw the structure of carbon, you have a carbon. That carbon is joined to another hydrogen, another hydrogen, another hydrogen. Remember the way we used to draw those to show how those how we were using circles to show how the atoms are joined to each other. So if you draw as the carbon as a central ring, then that central ring will have an intersection, or will have an intersection with a hydrogen atom, another intersection with another hydrogen atom, another intersection with another hydrogen atom. Remember, in the intersection, let me see whether I can be able to show it. In the what we are saying, like you will have, that is our main carbon, this is our carbon. For us to show how it's bonded, we used to draw like that. This is a hydrogen. And this is where the electron, one electron from carbon, one electron from hydrogen. And then the same carbon also will be joined by another hydrogen. So it has 3 hydrogen, and it will be joined by another hydrogen. Another hydrogen. This will be a covalent bond, covalent bond, covalent bond. So you can see that for sure, and you see this, that this has an, so you can see for sure this is a much larger molecule. And you can remember that all these are orbitals where electrons are supposed to be going around. So this, you cannot compare this with when, so this is now, remember this carbon is then joined to a nitrogen. So you cannot compare, yeah, so you cannot compare this, so not to a nitrogen, sorry, because it's, sorry, so it's joined to a hydrogen, the carbon, sorry, it's joined to this carbon, and this carbon is our alpha carbon. So you cannot compare this structure with another one. This is still alpha carbon there, and you have only a hydrogen. So this carbon here is only joined by one hydrogen atom. So you cannot compare this structure with this small structure. This methyl group is huger, it's much huger. It brings in steric hydrons. It bring in orbitals of electrons and steric hydrons. And because of these steric hydrons, or this large group, bulky group, it means after this carbon here, we have an NH, an amino group. Remember, for this drug to be metabolized, the enzyme that is metabolizing must come very close to the nitrogen, so that it first of all adds and it brings in an oxygen, and therefore you have a hydroxyl group, and then now brings about oxidative deamination. So this enzyme must come in and hide and metabolize this amino group or remove this amino group. So when you have this bulky group hovering around this amino group, it means this enzyme to come in, it must struggle to get space how to get in, because this methyl group is introducing steric hydrons. It is protecting. It is like if you have somebody who is huge, who is protecting you, it is not the same perhaps as having a thin person. So, that's what we're saying, that we have this huge group that is protecting the amino group and therefore prevents the easy, it is a red easy metabolism of the amino group, and therefore protects this drug from being readily metabolized by the monoamine oxidases. But they will still be metabolized because the enzyme will still maneuver and get you the amino group, but it will take a longer time. It will take a longer time. It is, and in taking a longer time, it means that drug will have it will reach higher concentrations because its rate of metabolism has been slowed down by introduction of a slightly larger group that protects the terminal amino group from undergoing oxidative deamination. So that is a steady activity at that particular point, where we are saying when we compare amphetamine to the beta phenyl ethylamine structure, the methyl group, because of its bulkiness, introduces steric hydrons and protects or prevents the rapid metabolism of the amino group through oxidative deamination. But ultimately, it will still undergo deamination. Now, when we talk about now introduction of another methyl group onto this group here now, we are saying again, we do not want to introduce a very huge group. If you introduce a very huge group, this amino group also is key in the binding. When you introduce a very bulky group, the bulky group, remember, this compound must go and anchor itself onto the receptor. So that's the receptor. So when you introduce very bulky groups, these bulky groups again will prevent the amino group, which interacts with the receptor through hydrogen bonds, to interact optimally with the receptor. So when you introduce very huge groups, they will now decrease the stimulatory activity because of introduction of steric hydrons, and whereby the compound is not able to optimally interact with the receptor. So I want you to understand the explanation of the two steric groups is a little bit different. For this one, the steric group is helping so that the metabolizing enzyme does not get access to the group it's supposed to metabolize, and therefore allowing us to have more concentration of the drug. And once you have more concentration of the drug in the periphery, it can be able to move quickly and get into the CNS. Now, when it comes to that, we are saying the steric hydrons is bringing about failure of this molecule to interact with the receptor maximally. When we put a small group like a methyl group, the steric hydrons is not much. And of course, what is the role of the methyl group? Of course, it will also hinder that group from rapid metabolism, but at the same time, it will also increase lipid solubility, and that molecule will have better activity. So I hope I've answered your question, that this methyl group there is protecting the amino group from metabolism. When we put large groups, of course, here, they will also bring steric hydrons so that this molecule cannot bind the receptor. That's why we stick to small group, which will only hinder the metabolizing enzyme and still allow for this molecule to bind the receptor. When you put huge groups like here, like the ethyl groups, the molecule is not able to bind the stimulatory receptor, but the other receptors. So it goes for another receptor, like the serotonin receptor, and therefore has anorexia activity. I hope that is clear. Is it? Is it clear, Cecilia? I hope it is clear. Water, is it clear? So Water, who had asked. You understood the concept of the steric hydrons? Water? Very good. Anybody else with any other question? Are we okay? Do I introduce the hallucinogenics, or what is your opinion? We have 18 more minutes. Or we will finish next time. What is your opinion? Do I introduce hallucinogens? Kwa nini mmenyamaza? Mkoaji, kwa nini mnanyamaza? Just, there is freedom. I told you the advantage of as we grow a little bit older. We are bit.
Hello,
Yes. We are more
I have a
accommodating.
question.
Yes, ask.
The difference between cathine, this one that is on the slide now,
Yeah.
and phenylpropanolamine. I've seen that they have a similar structure.
Which one?
This cathine and phenylpropanolamine.
You can see I've also called it noephedrine. So it is the same. You know
Okay.
that, so those names we give them like cathine and such, those are just the generic names, yeah? And if you look at the name I've also given it, you can see I've also called it, where was it? Noephedrine, all right? So I don't think there's any difference, okay? Are we together?
Okay, thank you.
Yes, and there's no difference. We are only saying it's like even this cathinone, you can give it a name, yeah? So some of these names are just like we talked about ampicillin. So these are even noradrenaline. These are names that you give as generic names, whereby that compound is just called cathine. These are the compounds called cathinone, but you can also give it a chemical name, all right? Any other question? Next time. Okay, we have the freedom. We have only one, I think we have only one topic to handle now, hallucinogens. And I think it's also good to handle it on its own because there can be some confusion. When we look at the SAR we have looked at the SAR of the beta-phenylethylamine. The ones for the hallucinogens are a little bit different. You'll be talking about the N substitution, and you find that the N substitution can bring differences when you talk about the hallucinogens as compared to the stimulants. Like even when we looked at the hallucinogens, some of them, like mescaline, we said we are talking about methoxy substitution on the aromatic ring. And for the same pathomimetic, we said it's not acceptable. So I think it's good for us to do it at a different time so that we do not have that confusion. So we need, because remember, we do have beta-phenylethylamine hallucinogens and also stimulants. We do have CNS stimulants, which are beta-phenylethylamine derivatives, and we have them as also hallucinogens. And I gave you psilocybin, and also I gave you the mescaline. So it's important for us perhaps to do it differently so that we do the compartmentation differently. So I think we have done enough for today. So next week, I think we should finish. I still owe you one explanation of the metabolism of enflurane and isoflurane, and I will make sure that I will summarize with that. I don't think there's anything else. So next week, God willing, and giving us the strength and allowing the power to behave the way it has behaved yesterday, I think the day before yesterday, and today, then we should be able to finish. Even if we don't finish a few slides and we are done. Most probably by the time we are doing your exam, we are done. I am seeing like what might happen. This is the narcotic analgesic. So CNS2 is usually not a very huge topic. And I think we have done well. Any other questions? So sign in. Thank you for your time. I hope you are reading. Hope you are doing your cards well. Other cards, you have really pushed me to the corner this time. Many push sana. Yeah, wacha tugojee Pharm Chem. Because we usually have an excuse that Pharm Chem is tough. But I hope by giving you that time, it will help you